So in today's video, we're going to be learning how to use a number to quantify the skewness of a distribution. And the first number, or we can say the first coefficient we are going to be considering, is actually known as the Pearson'S Skewness Coefficients. This method was actually discovered by a popular mathematician known as Pearson. Basically, what Pearson did was to use the mean, the median, and the mode, and also the standard deviation to get the skewness of a distribution. So that simply implies that when we know the interaction between the mean, the median, and the mode of a distribution alongside the standard deviation, we can be able to get the skewness, or we can be able to define how skewed a data is when compared to other data sets. That is, we can say, oh, that distribution is more skewed compared to that distribution, or we can say, oh, that distribution is more negatively or more positively skewed when compared to the other distribution. So before I try to give us the formula that Pearson used to define skewness, I would like to use an example to explain the simple concept behind getting the skewness of a distribution by having the value of the mean alone. You see, when you have the mean serves as the center of the distribution, and with that value alone, you can be able to visually tell whether a data set is either right skewed or is left skewed. So I would be using just a single example to explain how the mean can be used to get or to visualize the skewness of a distribution. So let's move into the worksheet. And here is our example. The question says, in a class, a midterm test was conducted and the result of the test is given below. So we have our results given to us as 11, 17, 12, 15, 10, down to 20. So this is our data set, and I want to know the skewness of this distribution. So I just want to use the mean to tell whether this distribution is either skewed to the right or is skewed to the left. I will not be having a number to quantify the skewness. That is, I won't be able to tell if the distribution is very skewed to the right or very skewed to the left, but I can just tell you that, oh, that distribution is skewed to the right, that distribution is skewed to the left. So the first step in doing this is to get the value of the mean of this data set, and that is very simple to do. So the mean of this data set is simply the sum of all the variables in the data set divided by the size of the data set, and the mean right here. So we have the mean is going to be the sum of everything that we have right here. So 11 plus 17 plus 12 plus 15 plus 10 down to 20, we have that to be equals to 429 divided by, so the size of our data set is actually equals to 29. So when we do the math, 429 divided by 29, we have our answer to be equals to 14.79, approximated to 2 decimal places. So we have the mean of our data set to be equals to 14.79, approximated to 2 decimal places. Now, the next step in trying to use the mean to tell how skewed a data is to actually rearrange our data set in ascending order. And by ascending order, I mean arranging the data set from the lowest variable down to the highest variable. So I'm going to be arranging our data set in ascending order, and when we do that, this is what we have. And this is what our data set looks like in the ascending order, that is in the increasing order. So the next step is for us to now locate the value of the mean in this data set that has been arranged in the ascending order. So our mean is 14.79, so that means that the mean is going to be somewhere around here. Let's just somewhere around here, this region right here. So that simply implies that is where the mean 14.79 is going to be located, between 14 and 15. So let me try to visualize this. So I can just make a space for this and then just simply say that the mean is actually 14.79. So that simply implies that this is actually the center of the distribution. So now it's time to know whether our data set is right skewed or left skewed. In the last video, I actually defined the right skewness and the left skewness, and I say that when a data set is actually right skewed, it simply implies that most of the distribution, or most of the variables rather in the distribution, cluster around the left, and the tail, which has fewer of the variables, points towards the right. And when the data set is actually left skewed, it simply implies that most of the variables actually cluster around the right, and the tail of the distribution with the lesser variables points towards the left. So knowing those 2 points, you're going to be applying it back to this question. So this is the center. Once again, we have some variables towards the right, and we have some variables towards the left. As we can see, we have more variables towards the right compared to the variables we have towards the left. So that simply implies that for this data set of ours, most of the variables actually cluster towards the right compared to the variables cluster towards the left. So that simply implies that we have more variables on the right than we have on the left hand side. So that simply implies that our data set is actually going to be a left skewed data. That is, this distribution is actually left skewed. So the disadvantage of using this method is based on the fact that we won't be able to quantify the skewness, but we can tell that this is definitely going to be a left skewed distribution. So how left skewed is this distribution is, and this is where the Pearson's skewness coefficient comes inside. So for us to quantify the skewness, we have to use the Pearson's skewness coefficient. We actually have two variations for the Pearson's skewness coefficient. In short, I'll be writing it as PSC. The first variation is the usage of the mean and the mode, and the second variation is the usage of the mean and the median. So the first variation, that is a PSC, is actually equals to the mean of the data set minus the mode of the same data set divided by the standard deviation. So this is the first variation, which includes the usage of the mean and the mode, and the second variation, which is this, is actually equals to, we have 3 times into the bracket, we have the mean minus the median divided by the standard deviation. Anyone you use to get your Pearson's skewness coefficient is actually going to give you the right answer. So that simply implies that for us to get the skewness coefficient using the Pearson's method, we need the value of the mean, we need the value of either the median or the mode, and then we need the value of the standard deviation. So I'm going to be using the same example to get the Pearson's skewness coefficient. So that means I'm going to be using this data set of ours to get the Pearson's skewness coefficient. So the first step is to get the mean, which we've done. So our mean is a 14.79. So I'll be using both variations. So the mode of this data set, we've gotten the mode of this data set. So I'm going to be linking a video on how we got the mode. So our mode is actually equals to 15. We've also gotten the median of this data set, and the median, which is this right here, is actually also equals to 15, and the standard deviation of our data set, we've also done that. I'm going to be linking a video right to that, is actually equals to 3.25. So we have the mean, we have the median, we have the mode, and we have the standard deviation. So we can substitute any of that. We can substitute all of that rather into any of the variations to get the skewness coefficient. So I'm going to take this a bit to the left so that we can have a little space. So let's use the first variation. So the Pearson's skewness coefficient is equals to, so the mean is actually equals to 14.79 minus our mode is actually equals to 15 divided by, so the standard deviation is 3.25. So when we do the math with our calculator, 14.79 minus 15, that gives us minus 0.21 divided by 3.25. So 0.21 minus 0.21 rather divided by 3.25, and we have our answer. So this is a 3.25 right here, and we have our answer to be equals to minus 0.065 approximated to 3 decimal places. Sometimes you can take it to 2 decimal places. So the Pearson's skewness coefficient of this data set is actually minus 0.065. Now this is actually a low negative skewness. The second variation, PSC, is actually equals to 3 into brackets, so the mean is equals to 14.79 minus the median is actually equals to 15 divided by 3.25. So 14.79 minus 15, that's a minus 0.21, times 3, that's minus 0.63, divided by 3.25, and that gives us minus 0.63 divided by 3.25, and the answer to this is going to be equals to minus 0.194. So the Pearson'S Skewness coefficient using the second variation is actually equals to minus 0.194. It makes sense that we are not having the same answer because the formula is actually a bit different from each other, but the answers simply still tell us that we have a negatively skewed data. So we need to know that the Pearson'S Skewness coefficient number can actually range between -3 and +3. So that simply implies that when the value, when the Pearson'S Skewness coefficient rather is tending towards -3, that is, we are having values like -2.8, -2.9. So that simply implies that that data set is actually very negatively skewed. And when we have values pointing towards the +3, that is +3, like we're having values like 2.5, 2.6, it means that that data set is actually very right skewed or very positively skewed, and at a skewness coefficient of -0.065 or -0.194, it simply implies that we have this little or no negative skewness in our data set. If you enjoyed this video and learned something new today, I would really appreciate if you can give this video a like and subscribe to this YouTube channel to get notified when I release new videos, which I do at least 2 times in a week. Thanks for making it to the end of this video, and we'll see you in the next one. Bye for now.